Assalamu alaikum friends. Today we are going to study about Huffman coding. Huffman coding is basically a greedy technique that is used to encode compressed data with least number of bits as compared to ASCII code encoding. So basically what you have to understand is that uh, Huffman coding, how you do Huffman coding. So in order to explain that thing, I have taken an example. The example says that there is a string or there is some sort of data in which the alphabet A is repeated 50 times, B is repeated 10 times, E is repeated 3 times, C is repeated 30 times, F has been repeated 2 times, and D is repeated 5 times. So if I add up all these uh, values, then this data or this message has total 100 number of characters. A is having the largest frequency, and you can see that F is having the smaller frequency, so on. Okay, so now how am I going to transmit this data? If I want to transmit it on via a transmitter, I need a space for 100 characters. You know that each character is comprising of 8 bits, so this means that you need a lot of space. So you know that whenever you transmit any sort of characters, you can transmit them in the form of zeros and ones. This is what we do in digital communication as well. So it means that you need to digitize these numbers in the form of zeros and ones. So one method that is very common and very basic, everybody knows about it, is the ASCII character encoding. In ASCII character, what we generally do is we have for 0 to 127 numbers, we say that we can represent them with the help of 7 bits. For 0, we say that 0 0 0 0 0 0 7 zeros can represent 0, and for 127 7 ones can represent 127, and so on for all the numbers which lie in between them. So if we follow this ASCII character encoding, then it means that for one character we need 7 bits, and for 100 characters, as is the case in our data, we will be needing 700 bits. These are so many bits, right? You can see that it is not easy to allocate space for 700 bits or transmit 700 bits. Okay, let's think about something else. Well, we can say that we can use 3 bits for each character, specifically in my data type, because if you say that you can represent A with 000, you can represent B with 001, and let me open it up so that the characters are easily visible. Okay, so for C we can say that you can represent it with 010, and D can be represented with 011, E can be represented with 100, and F can be represented with 100. So okay, it is possible that I can use instead of 7 characters, I can use 3 characters. So if I have 100 characters, as you saw that it was the case in case of M, we had 100 characters. So now in this case we are needing 300 bits. All right, but if the transmitter is such that even with 300 bits the transmission is not possible, then what should we do? So in that case I have to use Huffman coding. So now after establishing the fact that still I am in the need of lesser number of bits to transmit my data, I need some other technique. So let me now explain the methodology how I'm going to do Huffman encoding. So now Huffman encoding comes and says that we do it with even less number of bits. So first of all, you will select F and E and you can join them. Smaller will come on the left hand side and larger element will come on the right hand side. So you can see that F is the smaller element, so you can write it on the left hand side, and you can write down E on the right hand side. So this is the smallest number with the frequency 2. You can see that F was having the smallest frequency, and after that E was the second smallest frequency number that was repeated only 2 times. So it is written on the right hand side. And when we join both of them, then 2 plus 3 becomes 5. So in this way we can join these two numbers, right? Okay, so after that, what is going to happen after this? You can see that from your data, now you can simply cut E and F, and you can just write down a together value for these two, which is equal to 5. Okay, now after this you can see that which number comes second larger in terms of frequency. So of course you can see that D comes to be the second larger in terms of frequency. So you are going to make another branch just in line or parallel to this 5, because D has a similar frequency, or it could have been a bit larger as well. It could have been maybe 6. Still you would have been selecting D, but right now it's 5. So you can put D on this side, or you can put D even on this side, doesn't matter, but I have placed D on this side. Now if you join this 5 and this D together with two branches, so what will be the sum? 5 plus 5 is 10. So I have joined these two together, and this is the top, and the top includes the sum of these two. So now from the data I can even cut down this E and F, which is 5, and simply I can write down a value of 10. Yes, this D will also be cut down, because you have also included that D into your Huffman code. So in place of this D, E and F, I am simply writing down a single value which will be equal to D, E, F, and its value is 10. Okay, now let's see from your data that which number is the next largest and will be going to join with this string of D, E, F. So of course you can see that this B is the second largest. So in this step now I'm going to join B together. So you can see on your right that this was your first integration that you did, and this was your second integration that you did, and now right now just parallel to this 10 you will put B. I have made this B a little bit lower than this 10. Doesn't matter, you can place it a little bit higher, just parallel to 10, but even if you draw it like this, that's fine. The thing is that when you place B here, then you make two lines and join this 10 and B together, and what is the sum of this 10 and this 10? It is again 20. So this is just by coincidence that we are getting same numbers. Even B could have been a bit larger than 10. It could have been 11, 12, or maybe it could have been 9 as well. It could have been 9 as well. So in that case you would be placing B on this side of 10, and then you would be joining it like here. But right now since B is equal, so I can place it here or there, both sides, that doesn't matter. The real thing that matters is that you have to join this B with this 10, and the sum of these two is equal to 20. Okay, so we compare 20 with C, which is equal to 30, and write it on the right hand side of 20. Okay, now in the next stage you can see that even your B has been cut out, and of course your this D, E, F has been cut out. Now what you have got is something which is equal to B, D, E, F, and its value is equal to 20. Okay, so with this 20 you can either join this C, which is 30, and you can join this E, which is 50. Of course C is the closest with this 20, so we will join this C. And of course you can see that 30 is larger than 20, so the point that I have been elaborating since the beginning, that you will place it on the right hand side. So here you can see that this was your 20, and just on the right hand side of 20 you placed this C, and in the next step you joined this 20 and this C with two lines. Okay, and when you add them up, then 20 and 30 together will become 50, and in the next step you are left with only one data point, which is equal to 50. So you will simply place this 50, you can place it on the left hand side or you can place it on the right hand side, and you will join them with lines, and of course this 50 and this 50 will together make 100. So now you have exhausted all your data points, and you have made this larger tree in which you started with E and F. In the very first step, you joined them into this 5. You placed the next data entry and you joined them into this 10, and then you placed the next data entry and you joined them into 20, and then you placed the next data entry which was larger than 20, so that is why it came onto the right hand side. You joined them with this summation 20 plus 30 50, and then you added your last data entry which is 50, and you joined them with these lines, and 50 plus 50 made 100. Okay, now you can see that on the left hand side of the tree uh, you will put 0 numbers, and on the right hand side of the tree you will put 1 numbers. So you see that I have placed okay, let's start from here. So from this root, on the right hand side I placed 1, and on the left hand side I placed 0. Similarly, this is right hand side of this node 50, so I placed 1, and this is the left hand side of this node 50, so I placed 0. And now coming on to this node 20, so on the right hand side I placed 1, and on the left hand side I placed 0. Similarly, coming on to this node 10, so on the right hand side I placed 1, and on the left hand side I placed 0. Coming on to this node 5, I placed 1 on the right hand side, and I placed 0 on the left hand side. So this is what I have written here, that on the hand side of the tree, or all of all the nodes, we will place zeros, and on the right hand side we will place ones. Okay, so this is how we have labeled the complete tree. Now we are going to write the code for each node. So if I have these values or these data entries A, B, C, D, E, F. So for A, what will be your Huffman code? You can simply see where is A. So you can see that A is over here, and the code of A is 0. So you have written 0. Okay, now what is the Huffman code for B? So you can see that B is here. So the code for B will be basically the data points that you need to travel to B. So if I start traveling from the root, first of all I travel on this line, I get 1, then I travel on this line, I get 0, and then I travel on this line and I get 0. So 1, 0 and 0. So you can see 1, 0 and 0 is my Huffman code for B. Okay, so what is the code for C? So start traveling from the root again. So I get 1, then I go further, and again I get 1, and there I reached on C. So my Huffman code for C will be 1 and 1, because I encountered 1 and 1 when I was trying to reach C from the root. So this is 1 and 1. And similarly, my Huffman code for the data entry D will be, so just look on to D. I have got D here. So when I start traveling from the root node, it is 1, and then it is 0, and then it is 1, and then it is 0. So basically 1 0 1 0. So you can see 1 0 1 0. Okay, so what is the value or Huffman code for E? So you can see that E is over here. So you will get 1 0 1 1 and 1. So you have written 1 0 1 1 and 1. And in the last, what is the value for F? So you get 1 0 1 1 and 0. 1 0 1 1 and 0. So in this way you can get the Huffman codes for all of your data entries, because you know that all of your data entries have been entered into this Huffman tree. So you can find the codes for all of the data entries. So if you now want to write down the number of bits which are needed to encode all of these data entries, so you can see that for A, what is the how many number of bits are used? So it's only 1 bit that is used for A. And you know that how many A's were available in your data. In other words, I mean to say that what was the frequency of A. So you know that the frequency of A was 50. It was given to you in your data that A has been repeated 50 times in your data. So if for a single A you need 1 bit, then for all the A's you need actually 50 bits, right? Similarly, for B, how many bits are you needing to represent just one B? So you are needing 3 bits to represent a single B. And since you have 10 bits in your 10 B's in your data, so 3 multiplied by 10 will be 30. So you will be needing 30 bits to represent all the available B's present in your data. And in the similar manner, you can say that for representing one single D, you need 1 2 3 4. You need 4 bits to represent one single D, and in your data you have been given with 5 Ds. You can see that the frequency of D that was given to you in your data was 5. So you will multiply this 4 with 5, so it is 20. And for representing one single E, you need 1 2 3 4 5. You need 5 bits to represent a single E. And you know that there were 3 E's present in your data, so it will be 5 multiplied by 3 equal to 15. And to represent a single F, you need 1 2 3 4 5. 5 bits are needed to represent a single F, and you had 2 F's present in your data, so 5 multiplied by 2 is equal to 10. So if I add up all these number of bits, we placed okay, so we get 50 plus 30 plus 60 plus 20 plus 15 and plus 10. It makes 185 bits total. So you see that 185 is smaller number as compared to 300, or as compared to 700, as we considered the case in the case of ASCII code encoding or 3-bit encoding. So we are still needing less number of bits. And if someone asks you that what is the average number of bit to represent one single data entry in your data, then you will simply divide these total number of bits by the total number of characters that are present in your data. And you knew that you had 100 characters. It was given in the beginning that you have 100 characters, m was equal to 100. So you will simply divide this 185 by 100, which means that almost 1.8 bit is needed to represent any single average data character. Okay, one very important tip here is that we placed a on top, right? You can see that you have placed a on the top, like you considered it in the end, right? And you considered E and F in the beginning. What advantage you got by considering the lowest frequency characters in the beginning and the highest frequency character in the very end is that you for A, you needed the smallest path. This was the smallest path, so that is why you have got the least number of bits which you had to multiply with a very large frequency. If you had placed this a maybe like here, and a was here, and the path of a was this long, so with 50 you would be multiplying 5, and it would have been 250. It would have been a large number. So in Huffman encoding, the trick lies that always start building your Huffman tree with the smallest frequency numbers. First of all, you place the smallest frequency numbers because they are going to have a very long path, and in the end reach on to the highest frequency number, so that the path of the highest frequency number will be minimum and the path of the least frequency numbers will be large. So in this way you actually end up into having less number of bits. So that's all about Huffman coding. I hope you understand the methodology, how to find it, and I hope you can evaluate or calculate these Huffman codes for your data entries, and you have actually realized how shorter number of bits it gives you for encoding as compared to other techniques of encoding. And it's pretty simple, and it is very common because of its simplicity. And I hope you like the video. Then do like and subscribe. Thank you. Allah Hafiz.